Hello everyone. Yes, it's working. It's always, I've heard that it's always nice to introduce yourself before you talk, so I'll tell just a few things about myself. My name is Jukka Taimisto. I am one of the founders and software developers at SensorFleet, which is a Finland-based network security startup. I've been working with software, writing code for a living for over 20 years. Most of the time spent around network protocols. I never seem to get out of that space. I spent over 10 years writing fuzzers for various network protocols, wireless protocols like Bluetooth and stuff. I've written code in C, Java, Python, Go, and now for a few years I've been focusing more on writing software with Rust. This is my email address. If you want to ask me something later, you can grab me in the hallway. Today I'm going to talk to you about an architecture that we did for a software to read network packets to analyze them. We'll discuss the benefits of the architecture. We'll discuss benefits of the Rust as a language when implementing software like that. Then we'll talk about parsing network data, one of my favorite things to do. And then we'll discuss testing both the software and parsers. That's one of my favorite things to do as well. So let's start with the problem that we had, or the idea that we had. We wanted to create this sort of a probe that you would put in your network. It would listen to traffic from an interface. It would get the traffic to the interface, for example, from mirror port on a switch, or it could work on just like an active port. It would listen to this traffic and then identify devices communicating on the network based on their MAC addresses. So the basic question was what devices there are on this network. Then it would collect some information like how many packets were being sent, how many bytes were being sent by these devices, and so on. It would collect protocol-specific information like IP addresses used to communicate, and then what protocols are being used on top of IP, for example, or on top of Ethernet, and then collect some protocol-specific information from those. It would collect all this information about the devices and then publish periodic updates to a centralized manager, which then would be responsible for giving user a view about the network, what devices there are on the network, with the idea that you could place multiple of these probes on different parts of your network. They would collect the data, analyze it, and then send these reports to the manager, which then would give user a view about what devices they are communicating, give alerts if new devices pop up and stuff like that. Today we'll focus on the probe part. That's, for me, it was the most interesting one. The UI stuff is not what I can do. We had some design goals in mind when we started to implement the software. We wanted it to have simple architecture, like don't we all and always. We wanted it to be easy to expand with new protocol analyzers, with new functionality, so that we could start with something that works, like every startup does. We wanted to get something that works and then expand on it as hopefully customers ask for new features, or we needed to analyze new protocols instead of trying to build completely working system from the start. Instead, we wanted the architecture to be such a thing that we could expand it easily. And then we wanted it to allow handling multiple packets concurrently from the start. So in case that we needed to do multitasking or multi-threading, we wanted the architecture to be ready for that from the start instead of needing to rewrite. It usually is harder to rewrite or retrofit multitasking into our architecture. So we wanted it to have that ability from the start. We identified some components that we needed to write. Obviously, we need to be able to read packets from the network. We wanted needed a component to detect the communicating devices. Since we are doing detection based on MAC addresses, we needed to parse Ethernet headers and find out what devices there are, how they are communicating. We needed a component to do IP header analysis to collect IP addresses that the devices are using and protocol-specific information, like what protocols are being used on top of IP. And then, obviously, we needed a bunch of protocol analyzers to analyze for TCP, UDP, Profinet, whatever. And then we needed a component to actually create a synthesis of this information that we collect and publish it periodically to the centralized manager. So with these components and design goals in mind, we decided to try an architecture where we split the packet processing into a multiple interconnected tasks called observers. Divide these tasks between network layers so that we would have one task analyzing Ethernet traffic, one task doing IP level, and so on, so that the tasks are distinct. They have the distinct boundaries where they are operating, and then communicate between these tasks using Rust's MPSC channels, which allows easy and safe way to send messages between tasks. And then we decided to use asynchronous Rust for concurrency or for parallel execution, and Tokyo to provide the runtime. Tokyo because it was the most popular, and I think it still is the most popular async runtime. So the architecture for the packet processing looks like this. We have the packet reader, which reads the package from the interface. It pushes the package into the channel. There is an Ethernet observer which is running, listening data from the channel, analyzing the Ethernet header portion of the packet, and then passing the packet on to the IP observer so that the IP observer gets the packet starting from the IP header and analyzes that and detects what protocols are being used on top of IP, and then sends the packet or rest of the packet on to a protocol-specific analyzer. So that these can be run concurrently, so that whenever, for example, TCP observer is analyzing a TCP portion of a packet, Ethernet observer is already analyzing a new packet, and so on. So we have a simple flow of packets which can be run concurrently. So looking at the components in more detail, we have the packet reader, which is one of the simplest components. Its job is to receive packets, raw network data from an interface, and then forward this into a channel. All it does is runs in a loop where it receives packet from the network and then writes it into a channel. We decided to use a crate called luomu-libpcap, which is a Rust wrapper on top of the popular libpcap open source library that is often used to read packets. libpcap already provides all the primitives to read data from the net, and luomu-libpcap provides a Rust wrapper. It also provided us with asynchronous wrappers so that it was easy to use in an asynchronous context as well. The packet reader has a signaling channel that can be used to stop it. I'll talk about that a bit later, but I wanted it to have some kind of signaling that can be used to stop the packet reader when user wants to stop the software. But other than that, it just works in a loop where it reads a packet and forwards it. Then each observer has a same kind of design, same kind of structure. They all run on their own asynchronous task. They all receive packet from the channel. And when they receive the packet, they work on it, do some analysis. They get some metadata about the packet, timestamps and such, and they analyze the packet, the contents on their layer, on what's on their responsibility, and then send the packet on. Once they are done, they send the rest of the packet on to the next observer in the pipeline. So the design was quite simple for all the observers. They have all like similar functionality. They read a packet, analyze it, and then push it on to the next observer on the line. When the observer receives a packet from the channel, they own the packet. So you know that there's no one else can mess with the packet, because when it comes from the channel, it's owned by the observer. Observer can do whatever it wants with the packet, and then once it's done, it sends it on its merry way to the next observer. There's no locking needed between the observers. They just communicate by sharing data, so that the packet is traveling along the pipeline. There's no need to have centralized locking, for example, for packets. We know that there are no references to the packets. If once we collect the information, we copy that information, obviously, but we do not need to copy the packet. Only once when the packet receiver reads the packet from the network, it needs to make a copy, and that same copy travels along the whole pipeline. Since observers are run on their own task, they own their own state data as well. So there's no need to have global states, which would once again require sometimes complex locking schemes. So it's quite easy to have, because those observers all have their distinct task, they all can have their own state, and there's no need to share any state between different observers. So the architecture becomes quite simple in that sense. The job of the observers is to collect information. We call that information observations. Whatever they collect, be it MAC addresses, IP addresses, protocol numbers that are being used, DHCP parameters and stuff like that, all this is observations. And instead of having a centralized database where all observers are putting their observations, we decided to add yet another set of channels and yet another task to handle those observations, so that each observer can make their observation, publish them as soon as they are made, and then we have another task to handle them. So the architecture became to look like this. The packet pipeline still flows along, and then each observer, whenever they make an observation, whatever information they collect, that information is then passed on to a channel, to a reporter task, whose duty it is then to handle creating aggregates of the data and creating reports of the data. So no need to have centralized database, only pipelines, which I kind of liked. The reporter task in design is very similar to observers. It runs on its own async task. It runs on a loop where it receives data from a channel and handles that data. This time the data is not packaged, the data is observations. And reporter is the only task whose responsibility it is then to create the aggregate of the information that we have collected from the observer. So each observer publishes its findings, and then there is only one task which needs to be able to handle all these observations, collect all this information, create aggregate reports. And reporter task then periodically creates a report about activity seen in the network, what findings there are, what devices, and associates all the information for each device seen on the network. It needs to keep the collection alive only as long as the reporting period. So every time it has reported something, it can forget about everything and then start collecting new information. So looking back at the design goals, the architecture is quite simple. We have a clear separation of components. Each component have their own distinct task, what they need to do. So it's easy to design or easy to expand, because we can add new functionality to one observer without the need to touch any other observers. The architecture allows that we can easily work on single observer or reporter if we want to add new functionality. If we want to add new protocol analyzers, we can just add new observers to the pipeline. Or if we want to do, for example, TCP frame analysis for the TCP data and collect all the TCP data from one single TCP connection, we can add yet another observer to do that. So it's quite easy to expand and add new functionality, add new components to the system. And Tokio takes quite a lot of burden away from us. We do not need to worry about scheduling the tasks between CPUs. We do not need to care about how many runner threads we need for this particular platform. Instead, Tokio provides the runner threads. It provides the execution of the tasks on these runners. So it takes quite a lot away from us, and instead gives us just a platform we can use to run these observers. And in my opinion, one of the best things that Rust gave me, especially when working with data like this in this type of environment, is Rust's ownership model and the borrow checker. They kind of provide you these guardrails that you cannot do stupid things with the data. You cannot have references which outlive the actual data. The compiler will yell at you if you are making stupid mistakes or if you are trying to do something stupid. The ownership model kind of guides you into thinking about data. That's how I see it. And I have found myself often asking that what would Rust say about this when I'm programming in some other language where there are no guardrails which protect me. And I'm thinking that how should I do this in Rust, or how I would do this in Rust? Would the Rust C yell at me if I did this when I'm working in some other language? So I have found out that the Rust's ownership model is something that you should embrace. It usually kicks us every once in a while, and it yells at us quite a lot, but it's still like it wants to do good. And it tries to drive us into more simple solutions. I have found that sometimes when something seems too hard to implement, it's just Rust's way of saying that think again. There is a simple solution. Try some other way. And while not unique to Rust, the channels are really helpful, especially when you're dealing with concurrency and you need to share or pass data between tasks. Channels help you there. And once again, the Rust's ownership model helps you because it guarantees that the data that you are going to send is safe to send. Otherwise, it will once again yell at you and tell that this is not synced or this is not sent or something else. It gives you these error messages guiding you to what to do. So at least I myself have found this to be one of the best things about Rust, especially when you are working with data. We are using channels with capacity to provide some buffering between the observers, so that if one observer is running a bit more slowly than others, there is some buffering available for us. So the channels provide this buffer space. And then if there are spikes on the traffic, for example, then the buffering usually takes care of that quite easily. But if the situation kind of persists, if there is a longer term thing going on, then you will have to deal with rate limiting. You will have to deal with what if some observer cannot keep up. There are two ways to handle the situation. One is to block on send, which means that when we are trying to push the packet to the next observer, we have to wait until the observer is ready to receive more data, until there is once again room in the channel. That obviously slows down the pipeline. If the situation goes on for a long time, the observer starts slowing down because each observer in the pipeline will eventually slow down. Or another way to handle this is to use try send, which gives you a nice error that the channel is full, I cannot send it at this time, and then you can decide to drop the packet. Sometimes it's just better to drop the packet, accept that we cannot analyze all the data, but we at least got this far. So there are two different ways to handle, and you can use different types of channels between different observers to ensure how you want to handle the things. I found that it's very nice to have used, for example, type aliases to define different channel types that are used between the different observers. And then when you need to refactor, or if you need to change the behavior of the channel, you can just change the type alias to point, for example, blocking to a dropping channel. So this allows you to more freely try different things without the need to refactor the observers themselves. This also obviously allows you to change, for example, channel characteristics like the capacity of a channel from a single place, and instead of once again refactoring the observers or needing to change multiple places. The model also allows fanning out in a sense that you can run multiple instances of the same observer at the same time. So for example, we can run two different IP observer instances, so that the Ethernet observer needs to be modified so that it knows how to schedule the packets between these IP observers and can then send data, for example, in a round-robin way, so that each other packet goes to one IP observer and the next packet goes to another. And we can use the type aliases introduced previously. We can use those type aliases to provide a distributing channel that knows already how to schedule packets. One note there is obviously about internal state. So if you are running multiple instances of a same observer and it has some kind of internal state, you need to protect that state from concurrent access. And obviously the Rust C once again will yell at you until you do so. So it's kind of obvious that you have to do that, but Rust once again gives you this nice advice that you must do it. And you can use mutex to protect the state. I'm quite a lot of talking about log-free and log-free this. I'm not advocating against not using logging. Logging is good. You can use mutexes when you need to. But usually I have found that whenever you do designs which have complex logging, it usually leads to deadlocks or things that are harder to implement because you need to take care of logging order. So that's why I like to have things that are log-free instead of starting from multiple logs at the start. But I'm not advocating that you should never use logs. Obviously, mutexes have their place, and they are good for that. I'm kind of old school in a sense that I like my software to shut down gracefully. So whenever the user asks that you should shut down, I like my software to clean up, stop all the tasks, and then do all the final cleanup work, return a nice error code, and stop running. And this model allows me to do that because it provides kind of a natural termination signal for all the observers. The observers are running on the loop where they receive data from a channel. And once a sender to that channel gets dropped, the observer will get an error in the receive function indicating that channel has been dropped, there won't be no more data coming. So the observer knows that it's time to shut down. There won't be any data coming, so there's nothing more for the observer to do. So if you are using, like us, channels with capacity, it obviously might take some time before the error comes for the channel to train, but the error will come, the signal will come, and there is a nice signal to stop the system. So to do graceful shutdown with this architecture, we just hook up the signal handler so that whenever user gives us a signal to terminate, we signal the packet reader so that it's time to stop reading packets. That's why the packet reader has the signal. Then the packet reader will stop running. It will drop its sender it has for the Ethernet observer. The Ethernet observer gets an error. It shuts down, dropping its senders and so on. So it creates this kind of cascading effect where all these tasks are stopping one by one when they get the error. And when all the observers have stopped running, they have stopped their handles for the observation pipeline. So the reported task will get an error indicating that no more observations are coming. Reported task knows that it's time to shut down. So in the main of the program, we just hook up the signal handler to signal the packet reader, wait for all the tasks to go down. We know that all tasks have now finished running. They have cleaned up, closed all the handles they might have, and then we can do a final cleanup and return a nice error code to the user indicating that we have stopped running. Then this model allows easy splitting between unit and system tests. Because each observer has its own responsibility. It has well-defined set of inputs that it's expecting. It has well-defined set of outputs that it will be providing. Namely, it wants to receive the packet from certain level and it wants to provide some output, the observations. So we can unit test each observer separately so that we can concentrate on testing that observer's functionality. We just provide with some packet and context and then expect some observations and right kind of packet from the output channel. When we are testing observer functionality, we should focus on the observer functionality. We obviously have to do negative unit test cases as well, send invalid data to make sure that the observer doesn't panic, doesn't stop running or return invalid values. So negative test cases here are important as well, but they should focus on testing the observer functionality. We'll get to testing packet parsers. They should be tested separately on their own, and instead in unit testing observers we focus on the functionality of the observers. Then we can do what I call system tests, meaning that we can create different types of pipelines, connecting multiple observers together, then feed them some kind of network data and expect right type of observations to come out. So we can test different types of scenarios, string together different observers, the whole observer pipeline, take away some observer from the end and ensure that data flows properly. Each observer gets the kind of input that they are expecting. We just provide it with the packet and then observations are coming out and ensure that right kind of observations are coming out. We can test different scenarios, also test, for example, between blocking and dropping behavior of the packet channel and so on. Here, having a test system with some kind of harness or system which allows you to easily create context, because you need to set up quite a lot of stuff would help. There is a RS test crate at least which provides this kind of functionality where you can do pre-set up, properly set up things, but with the normal Rust test system this is doable as well. Then few words about parsing packets. This is obviously one of my favorite things. I've been doing this for quite a long time. So what I mean by parsing package is that we receive data from the interface. The data is just a string of bytes in a buffer. There's no structure to the data yet. And when we are parsing data, it means that we need to interpret the data somehow. That's where the specifications come in, and you usually get quite used to reading RFCs when you are parsing different protocol data, because that's where it's defined, not only the behavior of the protocol, but the layout of the data in the messages being transmitted by the protocol. So you need to read the specification. It usually tells you what kind of fields there are in the messages, how those fields need to be interpreted, and then we need to parse the data, interpret those fields from the data. There's a lot of things to consider. There are byte values, there are multi-byte values when you need to know what the byte ordering is for the data. There will be constants, like there are some type fields which are interpreted as an integer but have a limited set of values that are acceptable, and the rest of the values are not. You need to validate those values that whenever you are parsing data, no one is sending invalid values there. And then there will be a lot of substructures. Usually the packets are divided into substructures, which are then something like repeating TLV structures, type length value structures, where you get one length wrong and then you are just like off you go in the completely wrong direction. So there's quite a lot of things to juggle, quite a lot of things to do. Thankfully, Rust will help us quite a lot. So one of the key things to figure out is to how much data we need to read, and then how much data there is available, and whether or not this data is available. And that's the place where quite a lot of these vulnerabilities, exploitable bugs live. You interpret some length wrong and off you go reading from completely different memory area, and next thing you know, someone is stealing your whatever from your computer. There is a lot of exploitable bugs have resulted from reading lengths wrong and interpreting the length value and reading data from somewhere that you shouldn't be reading, outside the buffer but in allocated memory and so on. While Rust is a safe language, we have all heard that, and it is true. Rust protects you from reading outside, for example, the allocated buffer, especially if you are using safe Rust. It protects you from that. But Rust being a safe language doesn't mean that you shouldn't care about the length fields and making sure that you know. Rust will panic if you try to read. It will cause your software to crash if you try to read outside the allocated buffer. So Rust being a safe language doesn't mean that you shouldn't care about the data length, or that those bugs aren't bugs. So Rust being a safe language means that those bugs are not exploitable, and your code probably won't have a vulnerability. It still means that there are bugs. They are bugs that you should fix and you should care about. So Rust being a safe language doesn't mean that your software automatically is bug-free. It just means that those bugs hopefully are not exploitable and you just crash. But at least my customers come to complain if the software crashes still, and they don't care if I say that Rust is safe, hey, come on, it's okay. So I still need to do the length checks. And for parsing data, we are using crate called untrusted. It's a nice little crate, provides a zero allocation, zero panic primitive for reading data from unknown source. It provides a kind of a buffer where we can read data. It keeps track how many bytes we have read. And then it provides a nice error value if we try to read outside the buffer. And this is one of the things that I love in Rust is its result type. So whenever we try to read using this crate, we have a buffer, we try to read data, and it's outside of the allocated area, we will get an error indicating that something is wrong. Then there is an extension crate for untrusted, because untrusted provides only way to read 1 byte or multiple bytes, and that's it. There is an extension crate called untrusted, which then extends the untrusted with the capability of reading different types of commonly used data types from the buffer, like I want to read unsigned 32-bit integer in big endian, and there is a method for that. Once again, it returns a result indicating whether or not it was able to read those 4 bytes, whether or not they were okay. And there is a method for reading IP addresses and stuff like that you usually need when you are parsing packets. So what I usually do when parsing data like this is to use the result type and then the question mark operator to fail fast, because usually this is an example of parsing a TCP header, and usually if, for example, I'm not able to read the acknowledgement number, it means that I have miscalculated some length somewhere. I have assumed that there is data available in this buffer when there is not. And if I get an error, it means that there's no point in continuing because I know that I'm already messed up or the packet already was invalid. So there's no need for me to try to parse anymore. It's usually safe and best to fail as soon as you get some condition that indicates that you have miscalculated something or there is an invalid packet. So it's completely allowed to send a partial TCP header in the internet. No one is governing that, so you have to be prepared for everything, obviously. Then another thing I like to do is to add enums and or new type structs to add some type safety and especially validity checks. This is an example of parsing a DHCP option. There is an 1 byte option code which is defined by the specification to be 1 byte, and then there are some values that are allowed, some values that are valid options, and then rest of the values are not. We can use the enum and then try into, so that we try to parse the byte from the buffer. If it's there, it's good, and then we try to convert it into a enum. And if the conversion fails, that's where we can do the validation. So when we are converting, the try into will check whether or not this value is something that is allowed by the specification, and then we know that it's allowed. So whenever we get an enum back, we know that it's okay, it's in the range. We can use that. Using enums or new type patterns also adds type safety into your code. So if you need to pass this information somewhere else, it's just an integer, so if you are passing integers around, there's no type information or context around it. You do not know whether or not this was already validated, or if this really was and type failed and not some mishap. So it's much safer to use these enums as a type safety mechanism, so that you will pass always these enums to parts of the program that expects to have DHCP option code, for example. And it makes code more readable. At least I like to read what it means instead of looking at the integers. You can obviously use constants for that as well, but other benefits from this model also I think are far better than using just constants. And then once again, the borrow checker is your friend here. If you want to pass some reference to some parts of the data, then the borrow checker will make sure that the reference cannot outlive the actual underlying data. Once again, yelling at you if you are trying to keep it too long. Then you know exactly when you need to copy data, when you can pass a reference. And the lifetimes will make sure that everything is okay. So I cannot tell this enough times. Then testing parsers. So these network parsers or any untrusted data should be tested extensively. And there's a saying that if it comes from the internet, it's probably malicious. So you cannot trust anything that for example, the specification says that these values are not allowed. When I was doing fuzzing and I talked with the client, I told him that, okay, we found this crash that we sent you too big of a packet. And the client told me that, but you cannot do that. The specification says that it has to be below this limit. And so that's one of the mindset that people still have, that because the specification says that this value should be this, nobody is ever going to send you an invalid data. So instead, whenever you are parsing data, especially from the internet, especially from untrusted source, you should treat it as probably broken. And if it's okay, that's a good thing, but it's probably broken, or someone is trying to trick you into doing something with it. So have unit tests for your parsers. Write positive unit tests to make sure that you pass the right values, you interpret the data right, you get right kind of values out of it. But don't forget to add negative test cases. There are usually far more negative test cases than positive test cases. Add negative test cases to make sure that all your corner cases are covered. All those interesting places where data conversions or some calculations happen, make sure that they also handle invalid data. And then fuzzing really helps, especially when you are dealing with this type of data. Cargo fuzz is your friend. It will give all kinds of invalid data to your parser, and then it likes it to crash. So using fuzzing usually helps you find those completely out of the world cases which you never thought about could happen in the software. Usually given some time, the fuzzers are great, and that's why nowadays people are using them more and more, and especially when you are dealing with parsing like this type of data, which is easy to fuzz. It provides quite a lot of test cases, but it doesn't mean that you shouldn't do unit tests. They are still the cornerstone. Whenever you are refactoring, the unit cases are there to help you out, because usually you have made some mistake and so on. Or am I the only one who does that? So to conclude, the architecture with connecting tasks with channels, it allows nice composable architecture for example, packet processing, provides a nice pipeline that can be extended, modified easily, and Rust's ownership model, I thank a lot for it. I have found myself to be a better programmer because of it, and I like that it keeps me safe. And then when you are writing protocol parsers or parsing any data from an unknown source, always check your length fields and write some tests, and then add a couple of more tests. So, thank you.
Is any of this work available in open source?
The software itself is not, at least yet. I will still have to talk with my managers about that, but it's not like super secret IP of the company, but not at the moment, no.
Thank you.
Okay. You said you chose the MPSC mod channel. I ask why not broadcast? It seems more natural for this kind of.
For building the packet pipeline, we want like one-to-one almost channels, or from one to many, because we want to control that. But yeah, broadcast channels would work as well.
Oh, okay. Yep. Thank you.
Kind of maybe continuing on the previous question, I wonder if you considered, instead of doing a pipeline, to kind of like send everything to each observer and have them take the part of the packet that they want. I'm wondering, like, why, if you consider that, and why, what was the trade-off for you?
Yeah, well, because, for example, to parse TCP header, we have to parse the IP header and its options away from first. So then if we just pass the same packet to all observers, then they would all have to pass the same network layers.
Wouldn't that be faster though?
No, I'm not sure. I haven't tested, so, but yeah, I kind of thought that it's at least safer to have single place where I do parsing for a certain level.
Yeah, okay, thanks.
Thank you for this talk and very clear approach. I appreciate it. And I want to ask you if you ever considered the dynamic approach, the balancing with workload, so spawning and removing observers based on how much packets you receive on.
Yeah, that is something that the model allows. We haven't done it yet, but that is something that the model allows.
And also, when you said that you can also have multiple consumers, and you have to lock state because they have a shared state, and because you do scheduling on multiple channels. And is it possible to make routing instead of scheduling to make the state consistent with just single?
Yes. Okay. It's at least for some observers, for example, for TCP observers, we can ensure that packets belonging to a same connection always end up to a same observer. And if it only has state that is reliant on observations, then it doesn't need to have any locking. Yes.
Okay, thank you very much.
Another couple of questions. Regarding monitoring, you've built a pipeline, so any stall in the pipeline basically, as you were saying, propagates back eventually. Did you do anything specific to understand the workload and load on each stage of the pipelines?
Yeah, there are some statistics that we are collecting. So for like simplicity, I left out, but there are some statistics that we can collect, and we know how many packets are being dropped between some observers and so on, so we can observe the situation.
So, hello. Thanks for the talk. That was super clear and spot on. First of all, a small low-level thing. You said the packet is copied once at the beginning and then nothing more, which means it's boxed. Yeah,
it's a vector, basically.
Okay, perfect. And then about using type aliases with channels to experiment with different kind of channels. Have you considered using streams to abstract away the thing?
Yes, but haven't had time to do that yet. But yes, streams would be perfect. But
yeah, because in my architecture I actually ended up with streams, and I just removed those kind of things.
Yeah, that's true.
And the final thing about parsing, have you considered WOOFs, if you know what it is?
No. I like to build parsers and with the stuff. So that one of the best things to be in a startup is you get to decide what to do, and I like to do that stuff. But
Fair enough.
I know there probably are better parsers, but I like to build my own. So
thanks a lot.
Yeah, thanks.
Hi, great talk. I'm actually one of the libpcap maintainers. So one of the things in modern kernels is you get batches of packets. And I guess I heard from your answer that you're copying at least once from the pcap ring to yours, but not again. Would it benefit you to be able to not do that copy and also to spawn off multiple first layer observers on different CPUs simultaneously? That would be a...
and well, this software is more aimed for smaller networks where you actually want to know every detail.
Right.
So here the performance isn't that, but we have some other products which do kind of that with tpacket version 3 instead of libpcap to spawn.
Right, directly down to it. Yeah, most of these things are limited by CPU memory bandwidth, and so any copies are super expensive. Right.
Questions?
Thanks. I saw you were using an MPSC unbounded sender and receiver. What is your opinion on bounding MPSCs?
So usually like I said, we use channels with capacity, and unbounded is you do not know how much memory you are going to use. So I would suggest that in situations where there can be a lot of memory being consumed, say there is a DDoS attack or something like that, so never use unbounded channels, use high bounds if you want.
Anyone? Anyone? Okay. So, I got a little announce for you, but before that, thank you, Jukka.
Thank you.
Jukka Taimisto.